Okay, we get started again. All right, so that's stable species, and that's how we get thermodynamics of stable species. But what about radicals? So we can estimate or calculate the thermodynamic functions of radicals based on bond increments or bond association values for enthalpy, entropy, and heat capacity. Okay, so if we look at this reaction, we have a stable molecule giving two radicals, well, a radical and a hydrogen atom. So we have, in this case, we have a CH bond breaking. Okay, so let's just take, for example, ethane. So we have C2H6 gives C2H5 plus H. Okay. Okay, and we have delta H reaction. Okay, so by definition, what is the heat of reaction? Delta H reaction is equal to what for this process? The heat of reaction is what by definition? Okay, so it's the difference of the heat of formation of the products minus the heat of formation of the reactants. Okay, so it's delta H reaction is delta H naught F C2H5 plus delta H naught F H radical minus delta H naught F C2H6. Okay, the heat of formation of the products minus the heat of formation of reactions is the heat of reaction. Okay, but what is this reaction? Specifically, what is the reaction? Okay, it's the breaking of CH bond, forming the radical. So that's what. So what is? It's defining that CH bond strength, the bond association energy. The reaction is breaking that bond. Okay, so we're getting the bond strength of that CH bond. That is the heat of reaction. Okay, so, and this is what we define as the bond association energy. Okay, so I gave a specific example here, but this is the general example. Okay, so we have RH, okay, which in this case would be ethyl plus H. Okay, so we have ethane, okay, and delta H reaction is actually the bond association energy to break that bond. We could easily write, just as easily, write C2H6 gives CH3 plus CH3. Okay, so what's that going to be? Delta H reaction. Bond association energy for the CC bond. Exactly. But there's different species involved in that, so we're going to have different thermo involved. So delta H reaction is going to be heat of formation of methyl plus the heat of formation of methyl minus the heat of formation of ethane. It's not going to be ethyl and H anymore. It's going to be methyl and methyl. Okay? So different thermodynamic parameters, different delta H reaction, different bond association energy, because it is a different bond. Okay? So you can get bond strengths with this. And I'll show you tomorrow or Wednesday how actually from kinetics you can get sometimes thermodynamic parameters of radicals. Okay? So if I go back for a second, what I mean is here we talk about bond colorimeter, and we can get heats of formation of stable species. So you can put ethane in there and get that. But how about putting methyl radicals. Can you ring up Sigma Aldrich or one of these suppliers of chemicals and say, can you please give me a bottle of methyl radicals? I want to measure the heat of formation of them. Okay? You can't. Okay? So we have to have other ways to do it. The bond dissociation energy is different. It's different. Okay? And I'll show you that in a minute. Okay? Good question. So I was asked, is the bond dissociation energy in methane the same as it would be in ethane or in propane? It's slightly different, okay, because the local environment is different. Okay, we'll see that in a minute. Okay, so we have that, then delta H reaction is the heat of formation of the radical plus the heat of formation of H atom minus the heat of formation of RH, which I have written here in the specific case of ethane. Okay? Or we can say then the heat of formation of the radical, we just reorganize, we rewrite this, okay, BDE, which is delta H reaction, plus the heat of formation of RH minus the heat of formation of H atom. Okay? So if we have then, so to get the heat of formation of the radical, we have to first produce the heat of formation of the molecule. Okay? And then we can take this BDE into account, and knowing the heat of formation of a hydrogen atom, we can get the heat of formation of the radical species from THERM. Okay? And that's what we do. Okay? So we build in to our BDE group, our BD group, so that we can calculate the heat of formation of the radical species. We'll see it in action a little bit later. And you can look at their text files in THERM, so you can actually see the numbers and everything and how everything works and figure it out for yourself. So just play with it and you'll see. All right? Okay, so here, this is what you were just asked. Okay? The strength of the CH bonds depends on the stability of the radical. So for ethane, for instance, a hydrogen atom in ethane, typically it's about 101.1 or 101.5 kilocalories per mole. Okay, for the hydrogen in the center on propane, for instance, secondary hydrogen atom, the bond energy is about 98.5 kilocalories per mole. Okay, and on isobutane, the tertiary hydrogen atom is typically 96.5. Okay, why? Because here the carbon to which the hydrogen is bonded to just one other carbon. Okay, so the bond strength is higher. For methane, the bond strength is about 104.5 kilocalories per mole, because the carbon has no other carbons. It's just 4 hydrogens, and so all the electron density is in each bond. Okay, here this carbon is bonded to another carbon, so this withdraws electron density from this one and weakens it relative to a methane by about that much, 3 kilocalories per mole. You have this carbon is bonded to 2 other carbons, so this CH bond strength is weakened by another 3 kilocalories per mole. Okay, so now you're down at 98.5, and now this carbon is bonded to 3 other carbons, and so the hydrogen that you're abstracting is weaker again by another 2 kilocalories per mole. So it lowers it by about 2 to 3 kilocalories per mole each time. That's the trend. Okay, so and carbons aren't all that electron withdrawing. What if you have an oxygen atom? Okay, or sorry, I jumped the gun a bit. Okay, here, say you have something like 1 butene or 2 butene. And actually, if you abstract a hydrogen atom here, a primary allylic, or we can say a secondary allylic, we end up with this resonantly stabilized structure, which is the same molecule from both. Okay, either 1 butene or 2 butene. Okay, so this would be a primary allylic or a secondary allylic. But a primary allylic hydrogen atom has a bond strength of 88.2 kilocalories per mole. It's much weaker. So a primary here is 101.1 kilocalories per mole in an alkane. In an alkene, a primary allylic is 88.2, much weaker. Why? Because when you abstract the hydrogen atom, you get this resonantly stabilized structure, and so it stabilizes the system. Okay? And once you get that resonantly stabilized structure, it's long-lived, and so it likes to, and it makes it easier to form that structure. Okay? And it's way easier than a typical primary hydrogen atom. Okay? By, what is it, 13 kilocalories per mole. Okay? Lower. Easier to abstract. Okay? And as I said, if you have an oxygen atom then, okay? So here, in ethane, the bond dissociation is 101.1 kilocalories per mole. For a hydrogen atom bonded to a carbon, which is bonded to an OH, the oxygen atom here draws electron density away from the carbon, weakening the CH bond. And so the hydrogen atom in either methanol or dimethyl ether, the bond dissociation energy is 96.2. It's like a tertiary hydrogen atom, not a primary. Okay? So we have these tables of bond dissociation energies that we can formulate. Okay. So group additivity can be applied to pretty much anything. Okay? We can have alkanes, alkenes, and alkynes, alcohols, ethers, ketones, aldehydes, cycloalkanes, aromatics. Okay, but we parameterize, and we're constantly, in my group, updating the bond contributions based on the most accurate thermochemistry values that are available to us. Okay, and it's very difficult to keep on top of everything, actually, as it comes in the literature and so on. But we do the best we can to keep everything as up to date as we can, okay, and have the most accurate thermochemistry that we can for the species because it affects the kinetics so much. Okay, so there's different kinds of atoms that we define, okay? So we have a carbon. So if a carbon is sp3 hybridized, in other words, if it's in an alkane, like in ethane, propane, butane, pentane, any alkane, if we have a carbon there, it's just C, okay? So for instance, the carbons, we've got two carbons in ethane. We have C bonded to C bonded to H3 twice, okay? And in butane, we had C bonded to C bonded to H3 twice, and we had C bonded to C2 bonded to H2 twice, okay? But it's just carbons in alkanes, okay? A CD then is an sp2 hybridized carbon atom. And sp2 is just an alkene, right? So like ethylene. Ethylene will be CD bonded to H2 twice. Okay. So here we have ethylene. So we have H2, H2. So this will be CD bonded to H2 twice. What about propene? C bonded to C. We have H2, H3. So we have 1, 2, 3 heavy atoms. How do we define this? We have CD bonded to H2. Okay, that's 1. Sorry, I'll be a little bit more. CD bonded to H2. Okay, what else do we have? We have this. There's a H here. So we have CD bonded to C bonded to H. Okay, so this is a CD bonded to C bonded to H. And then we have a C bonded to a CD bonded to H3. So we have C bonded to CD bonded to H3. Okay, and that's the 3 heavy atoms. We have 3 different groups, 3 heavy atoms defined for propene. Okay, so, but The CD is an sp2 hybridized carbon, not sp3. Okay? And then we have triple bonded. So in propine, you've got a triple bonded carbon. Okay? And that's an sp hybridized carbon atom. One triple bond. Okay. And then we have Ca, an allene-like carbon. So you've got a carbon here with a double bond each side. We call that Ca. Okay? And Cb will be a carbon atom in an aromatic ring, a trivalent carbon. Okay? Carbon atom in an aromatic ring. And then you've got Cbf. This would be a fused carbon atom belonging to several aromatic rings. So if you had naphthalene, for instance. Right? So what we're talking about here, sorry. Okay, so this would be CBF. This one and this one will be CBF. So this is a CB, this is CBF here. Okay, so these are fused. Okay, just to distinguish between them. And then we have superatoms. Okay, so how do we define acetaldehyde? So we have CH3CHO. How do we describe that? It's C bonded to C bonded to H3. And then C bonded to C bonded to H bonded to O. And O bonded to C. It doesn't make sense, right? So what we do is we treat it like this. Okay? We look at it like this. Okay? And we treat this as a super atom. Okay? So we have C bonded to CO bonded to H3. And then we have CO bonded to C bonded to H. Okay? And that's how we describe acetaldehyde. And then we can treat other groups as well. You have NO, NO2, SO2, PO, and so on. Okay? So I'll be doing some anyway. We'll do some examples. And you'll become more comfortable. Okay? So here we have tables. And actually, this is a table then taken from Sid Benson's book. And it's actually, I still highly recommend that people. This is really the Bible of thermodynamics, okay? So if you can get your hands on a copy, it's gone out of print and in print a number of times, but I managed to get a copy years ago myself, okay? And here, actually, he lists the groups a little bit differently. In THERM, we list the groups in alphabetical order, okay? So C comes before H in the alphabet, so it's we describe it as C bonded to C bonded to H3 rather than C bonded to H3 bonded to C. I'm sorry about that. It's just the way it's done in THERM, but I hope that it doesn't lead to added confusion for you. Okay, it's the same thing. Okay, so you can see here now, and Sid's table. There's these appendices in the back of the book with tables of group contributions. Okay. And here's his, and these are in values, kilocalories or calories per degree Kelvin per mole or per mole, okay, depending on. So it's calories anyway, calorie units rather than joules. Okay, so you've got C bonded to C bonded to H3. This is the contribution to enthalpy, entropy, and then heat capacity at different temperatures. Okay, and in THERM, we have exactly the same tables. Okay, so THERM, if you look in the code, you'll see files called HC, HCO, and other ones, CYCO, and so on. So HC contains the group values for all carbon-hydrogen species. HCO contains all the ones including oxygen atoms. Okay? The CYC one contains cyclic structures. Okay? And so on. Okay? So you can see here then there's a different contribution for C bonded to C2 bonded to H2. Okay? But you can then use these, you sum them from the contribution in a molecule to determine the thermochemistry, the final thermochemistry of the total molecule contribution. Okay, so let's do it. Let's do isooctane. Okay? And it's not as simple as I've been making out. It's even more complicated. Right? So now you think you know it all. We're only about halfway there. All right? Okay, so let me do it this way. It's a little bit complicated the way it's done on the board. It's kind of mind-boggling. Let me just draw it. And if you don't mind, I'm just going to draw it like this. C, 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 C. I'm not going to include the hydrogens. They're included here for you, but I won't include them on this one, just to keep it simple. Okay? And it might be easier if you look at it this way. So we have, what is this? This is a carbon bonded to a carbon and 3 other hydrogens. And we have 1, 2, 3, 4, 5 of those. Is that all right? So we have, let me write it here, C bonded to H3. And we have 5 of them. Okay? And then we have a C bonded to C4. C bonded to C4, and we've just one of them. Then we come here, we have a C bonded to C2, bonded to H2, and we've one of them. C bonded to C2, bonded to H2. Okay? And finally then we have a C bonded to C3, bonded to H. So C bonded to C3, bonded to H. Okay? Now, have I included everything? Have I missed anything? And so let's count it. What is group additivity? It takes the heavy atoms into account. How many heavy atoms do we have in isooctane? 8. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay? So how many groups do we have? We should have 8. Okay? We have 5, 6, 7, 8. So I didn't miss any. Okay, so I've picked up all the groups. Okay, it's a good start, but we're not there yet. Okay, so we can get accurate, or we think. Okay, we can't actually, but from what I've told you so far, we can get accurate enthalpy and heat capacity values for the molecule just based on the groups. We can get accurate entropy. If we have the groups, we have to correct for symmetry. Okay? So the first thing, we have to do the symmetry correction. Isn't that right? Okay, so what is the symmetry correction for isooctane? It's written there. I wish it wasn't. If I just, well, it's written in front of you, but can I go back? And don't look. Okay? So what is the symmetry? You just look here. Okay, I just want your brain clicking. Okay? And just challenge yourself to try and do it. Okay? So what is the symmetry number for isooctane? And it's going to be different than what you think. All right? So anyway, well, maybe you'd be right. I hope you are. Okay, so here we have 3. Is that all right? Because there's 3 hydrogens. I didn't draw them, but okay. 3 times 3 is 9. Times 3 is 27. Times 3 is what? 81. Times 3 is 243. Is that right? So 243, right? But it's actually not right, okay? Because here, if we rotate around here, this is like a methyl. So there's another 3 here. So anytime you have a terbutyl, you have 3 times 3 times 3. So it's 3 times 3 is 9, 27, 81. Okay? Because you have a threefold 1, 2, 3. You see, if you rotate around this guy 120 degrees 3 times, you see the same environment. If I had a molecule of isooctane, and I asked you to leave the room, and I rotated around this CC bond 120 degrees, and I say, okay, come back into the room. Do you see anything different? And you wouldn't be able to see anything different. And then if I did it again and again, you'll never see any difference. So there's a threefold symmetry around this bond. So actually here, the symmetry is 81 times 9. Okay? So 81 times 9 is 729. So that's where we get the symmetry for isooctane. So it's 729. Okay? So we have to correct for that then. So we have to subtract minus R log 729 from the entropy contributions from each of these groups to get the entropy of isooctane. Now, in theory then, we're done. We have the thermochemistry of isooctane calculated. Okay? But we're still wrong. Okay? So everything I've told you so far, I've misled you. Okay? Well, I haven't. Okay? It's true for, what we've done is, it's true for N-alkanes. Okay? So let's take something like another molecule that I'm familiar with, N-heptane. Okay? If we take N-heptane, okay, and I'm going to draw it a little bit differently this time. So 1, 2, 3, 4. Okay? So that's N-heptane. Okay? Depicted. So we have C, 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 C. Okay? 7 carbon atoms. Okay? And if we do, so what are the groups for N-heptane? We just do it here. We have C bonded to C, bonded to H3 twice, and we have C bonded to C2, bonded to H2 5 times, I think. 1, 2, 3, 4, 5. 7 heavy atoms, 5 plus 2, 7. Okay? We have, what is the symmetry number? So it's 3 times 3 is 9. And if we sit in the middle of the molecule, we have twofold symmetry, so it's 18 actually. Okay? So the symmetry number of most alkanes is 18. N-alkanes is 18. Okay? So the symmetry number is 18. So it's going to be, if we want to get the thermochemistry of this molecule then, we sum the group contributions to the enthalpy, entropy, and heat capacity for 2 C bonded to C bonded to H3s, 5 C bonded to C2 bonded to H2s, and then for the entropy, we subtract R log 18, and we'll have accurate thermochemistry for N-heptane. That's true. No more about it. That's it. It's done. Okay? Using group additivity. But isooctane is a different kettle of fish. It's not an N-alkane. Okay? And what makes it distinct? What makes it distinct is this. Here, I'm going to now put in the hydrogen atoms. Okay? And draw the complication. Okay. And now you see these hydrogen atoms are proximate to these ones. Because of the branching in the molecule, you can't get away from that. Okay? And because they're proximate, the electron density around them will overlap with the electron density around the other hydrogen atoms, and that will increase the heat of formation. It'll make it higher than it would normally be in an alkane. Okay? Because they're proximate to one another and raise the energy. Okay? It won't be as stable. It's going to be less stable. Okay? Because of the proximity of those hydrogen atoms to one another. Okay? So what we have to take into account is these overlaps. Okay? And to take into account those overlapping, which affect the heats of formation, raising the heats of formation, like making them less stable, okay, we have Gauss interactions, first of all. There's two interactions that we have to consider, Gauss interactions and 1,5 interactions, okay? So I want you here, we're looking at the molecule here. So here's the terbutyl end, okay? And here's the isopropyl end, okay? And if we look at it, okay, this whiteboard is really too small, but I'll draw it up here now. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now, let's look across this bond. Okay. Okay. If we look across this bond, okay, we have, and we depict this carbon as a ball here, right? That's bonded to 3 other carbons. Methyl, methyl, methyl. Okay? And we look directly behind this atom at the other carbon atom. Okay? And what do we see? Okay? We can't see the other carbon atom at all. But on this carbon atom, we've got 2 hydrogens, and we have an isopropyl group. Okay? So there's a hydrogen, hydrogen, and isopropyl group. Okay? So we have no choice. We put an isopropyl, and then we put hydrogen, and we put hydrogen. So now, the hydrogens that are on this isopropyl group are always going to be proximate to the hydrogens on this methyl, right? Raising the heat of formation of isooctane relative to an N-alkane by that interaction, a Gauss interaction we call it, okay? And actually, it raises it in this direction and raises it in this direction. So we have 2 Gauss. Okay? So we have 2 Gauss. Okay? And we have no choice. Okay? Sorry, I'm talking about this one here. So here we have, I've just drawn it here. Here we have methyl, methyl, methyl. We have an isopropyl between these 2 methyls, or an isopropyl between these 2 methyls, or an isopropyl between these 2 methyls. If we rotate it through the 120 degrees, which we can. Okay? Regardless of where we rotate this isopropyl. So let's rotate through 120 degrees. The isopropyl will arrive here, the hydrogen will be here, the hydrogen will be here, and the isopropyl is always between 2 methyls. Okay? We can't avoid 2 Gauss interactions. Unavoidable. Okay? So if we look across this bond, we have to add 2 Gauss interactions to the heat of formation. Okay? And a Gauss interaction contributes 0.7 or 0.8 kilocalories per mole to the heat of formation. So that means that isooctane is going to have to increase by 2 times that to correct for this. Okay? But now if we look, so that's this bond. What if we look across this bond? Okay? And that's this situation. Okay? So if we look across this bond, let's look at that. It's depicted on the board there, but I find it easier maybe if you follow it on the whiteboard. I don't know. It's the same thing ultimately. Okay? So now we have this carbon and we look across this bond. So if we take this carbon, we have a hydrogen atom, and we have 2 methyls. CH3, CH3. Okay? And now this is bonded to a carbon, which is directly behind here. We can't see it. We're looking down that bond. Okay? And then that carbon is bonded to 2 hydrogens and a terbutyl. Okay? So now we can put a hydrogen here, and a terbutyl here. Okay? Terbutyl. So now the terbutyl only has 1 Gauss interaction. Okay? If we rotate through 120 degrees, we could have the terbutyl here, and then a hydrogen here. But then we would have 2 Gauss, because the terbutyl would be lying between the 2 methyls. Or if we rotated through another 120 degrees, we could have the terbutyl here, hydrogen here and here, but again, the terbutyl has 1 Gauss. And then, so you have to consider, by rotating through all the possibilities, which is the 3 120-degree rotations, and you pick the lowest one. And the lowest one has at least 1 Gauss. Okay? So depicted here are the 3 possibilities. Okay? Here, there's 1 Gauss. Here, there's 1 Gauss. And here, there's 2 Gauss. Okay? So there's at least, in these 2 cases, there's at least 1 Gauss. Okay? So you have to add 1 more for this bond. So there was 2 unavoidable Gauss interactions across this bond, and there's 1 unavoidable Gauss interaction across this bond, and that's it. So we have to add 3 Gauss interactions for isooctane. So relative to an N-alkane, to N-octane, isooctane has 3 times a Gauss interaction increase in the heat of formation, which is 3 times 0.7 or 0.8. It's, I don't know, it's about that. Kilocalories per mole. Okay? So we have to add that. Okay. Now, so that's a Gauss interaction. But actually, not only do we have a Gauss interaction, but then we have 1,5 interactions. So if we go back, maybe I get it. No. Okay. Okay, I draw it again. So we have 1, 2, 3, 4, 5, 6, 7, 8. And now we have here. Okay, 1, 2, 3. Okay, I'm not drawing the other ones. Okay, so if this is 1, 2, 3, 4, 5. There's a 1,5 interaction. Okay? So there's a proximity of these hydrogen atoms on this methyl being proximate to the hydrogen atoms on this methyl. That's what I pointed out earlier. Okay? And this is in addition to the Gauss. It's called a 1,5 interaction. Okay? So I'll just give an example where you have a Gauss, but you don't have a 1,5. And that's 2-methylbutane. Okay? So if we look at 2-methylbutane, 1, 2, 3, 4, 5. That's the first molecule for which you have a Gauss interaction. Okay? So if we just look at this guy for a second, if we look across this bond here, okay, we have CCH. So this is this carbon. It has C, C, and a hydrogen. Okay? And then this carbon has two hydrogens and a carbon. Okay? So we put a hydrogen here, and we put a carbon here. But no matter where, if we rotate through 120, we have two Gauss. That's not good. And we rotate through another 120, we still have a Gauss. So for 2-methyl butane, it's the first molecule for which you can have a Gauss interaction. And you have to correct that for the heat of formation. Okay? So if you look at 2-methyl butane compared to N-pentane, it will have a heat of formation which will be 0.7 or 0.8 kilocalories per mole higher than N-pentane because of that interaction. Always. Okay? But it doesn't have 1,5 interaction. Okay? So there's no hydrogens here that are proximate to a 5. Okay? They don't exist. Okay? Whereas here, we have an unavoidable 1,5 interaction. Okay? And actually, there's two of them. Okay. 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 So, well, it's one, but it's either or. Okay? So you have either this one or this one. But you always have an unavoidable 1,1,5 interaction. Okay? What if you had another methyl group here? You'd have to have two 1,5 interactions because now there would be an unavoidable interaction of the other methyl group with another methyl group on this side. Okay? And you'd have to include two 1,5 interactions. Now, you can rotate this through 120 degrees 3 times. So at some stage, you'll have the hydrogen out here, and you'll have two methyl groups in here. And you will have two 1,5 interactions. But will the molecule exist in that form or not? And the answer is no. It'll try to exist with the lowest heat of formation possible. So you should describe it with the lowest heat of formation that you can. So if it can exist just with one 1,5 interaction, then you just include one 1,5 interaction. You don't include 1.5. And say on average, it's 1.5 times rather than, or whatever it is. Do you understand? All right. So, and a 1,5 interaction is actually is much higher. It's 1.5 kilocalories per mole as opposed to 0.7 for a Gauss. Okay? But it's considerable increase in the heat of formation again and making it considerably less stable. Okay? And must be included. Okay, so now, after all of that, now we know what we're talking about, finally. Okay? So the group additivity, we define everything for N-alkanes. But for branched alkanes, then you have to make these corrections. The Gauss corrections and the 1,5 corrections, where appropriate. Okay? So you can, and here I have more modern values. So this group contribution for C bond to C bond to H3, slightly different from what Sid Benson had recommended, minus 10.2 in a previous table. I've changed it, okay, over the years. Okay, here we have C bonded C2 bonded to H2. Okay, so anyway, here's our 5 of these, you know, the different groups. So 5 times this, plus 1 times this, plus 1 times this, plus 1 times this. Plus 3 Gauss corrections, 3 times 0.7, and 115, we end up with a total of minus 53.54. It's a very simple calculation. Do it yourself. See that you get minus 53.54 and how it comes out. Okay? You'll see that it comes out. Okay, we add up the sum of the contributions for the entropy. Okay, we subtract R log the symmetry number, and this is our total entropy for isooctane. And then the heat capacity at 300, this is just the 300 value. You can get all the other ones by just summing the contributions. And that's it. Then you get the total thermochemistry of the molecule. Okay. So the software, as I said, I had this slide a little bit earlier, but the software I like to use still is THERM. There is a program online on the NIST database that you can generate thermochemistry using it. Again, it uses group additivity. Okay? There's the Thurgas code, there's Chromium also available. And of course, as I said earlier, quantum chemistry calculations now are used more and more. And typically what we do in Galway, my group, we take the quantum chemistry data that's available and try and re-optimize the group contributions so that we have accurate group values in THERM and the most up-to-date, so that we can generate thermochemistry for larger species. Okay, I know it's a little bit early, but why don't we take a break now on that? And then when we come back, for the last hour, we'll use THERM to calculate group or thermochemistry for different species, both stable and radical species. And you'll know how to do thermal then, okay? So why don't we come back 11:05, okay?